Okay, so last time we talked about the memory optimization at the global memory, at the layer of global memory, and we introduced the technique called the memory closest memory access. Okay, um, so to basic, it is optimization provided by hardware, right? It allows the request to perform the memory access in a collective way. So um, in order to take advantage of that, you need to serialize your memory access from all the threads within the WAP. Okay, so they can read in a closed region and issue the memory access in a single request. Okay, so you can do that by rearrange your memory access pattern. Okay, all right. And the second technique for reduce the global memory access time is to use the shared memory, as we have said it before, right? Which is because shared memory is much faster than the global memory. So if we can we can load the reuse data to the shared memory, then we can completely remove or reduce the number of global memory access, right? Okay, and so for that technique, it's just a concept, but to realize that concept, usually we rewrite our our code, follow the technique called the tailed algorithm. So it's a class of algorithm. It's a class of algorithm that realize the concept of load your reuse data to the shared memory. And because you have usually, right, the amount of data you want to you're going to need to access are way larger than the size of the shared memory. So you need to partition your data and load them into the shared memory one by one. And the order and how to partition it, that's the implementation of your tailed algorithm. Okay? So first of all, let's just look at the example, right? Why shared memory is so important for global memory? Okay, so this is a simple use case, right? Example for matrix multiplication. Okay, so we have three layers of for loops. Okay, and we perform this C equal to A times B. This statement. Okay. And the size of the matrix, let's say it's a n by n matrix. And it's the same size for matrix A, B, and C. Okay. So first of all, we want to see whether or how much, right? How much global memory access is performed in your code. And one way to measure that is called the compute to global memory access ratio, or short abbreviate as CGMA. Okay, and as the name implied, we try to measure the ratio, the number of computing versus the number of global memory access. Okay, and of course, because you usually memory is the bottleneck, right? So you want this ratio to be as larger as possible. Okay, so look at the example over here. Okay, so all the computation performed in the last statement here. Okay, so we can measure the ratio, just analyze this statement. Okay, so so for compute, so that's just simply count number of operation, right? And as you can see, we have one multiplication, right, and one addition, right? So that's two compute operations. And for memory access, global memory access, because we assume all the data is stored on the global memory. So the memory access is also two, okay, because you have to read the element from array A and another element from matrix B. So you have to read two elements. And as a matter of fact, you do have to write one element to C matrix, right? But because read and write bandwidths are separated on GPU, so usually you only need to count either read or write. Okay, so here, of course, is you perform more read than write. So the memory access is determined by the number of read access to your global memory. Okay, right? And because for the CUDA code, as you know, basically all the threads is performing the same operation here. So the ratio will certainly be the same across all the threads. So we can just analyze it by the behavior of single threads. Okay, and you can see that so in this case, the number of computations is 2, and the number of memory access is also 2. So the CGMA ratio is just 1. Okay, so that means as you can see, that means for every single computation operation require 1 global memory access. So this ratio certainly is not very good, right? And we need to find a way to increase this ratio in order to minimize the performance bottleneck on memory access. Okay, all right. And how much ratio do we want to achieve, right? It depends on, of course, the compute capability versus the memory bandwidth. And again, let's just take the Kepler architecture as an example. We analyzed this before, actually. If you remember, we can know the computing speed according to the flops, right? The flops performance from the hardware spec, which is almost 4 teraflops. And for global memory, its bandwidth is only 250 gigabyte per second. And also, every single floating point operation actually require 4 bytes of data minimum, right? So that means the amount of data consumed by your computing core should be 4 teraflops multiplied by 4, and then divided by the bandwidth of your memory memory access. Okay, so it's roughly about 64 times. So if the ratio GCMA ratio is less than 64, which means very likely you are bounded by the memory bandwidth. Okay. On the other hand, if somehow you get the ratio over 100 or even 200, then probably it is bounded by the computing capability. Okay, so in general, if you analyze any GPU code, usually it's hard to achieve the ratio we desire over here. So usually it's bounded by the memory. Okay, and also because in the newer architecture, usually it is easier to increase the computing power than the memory bandwidth. Because for computing power, you can just add more core to your processor. But for the bandwidth, if you at one hand, people want to have a larger memory space, right? On the other hand, if you have larger memory space, usually it will cause longer memory delay. So that's why we have those 3D stack memory technique. Try to reduce the distance from the memory chip to your computing core. Okay, so usually it's harder to reduce the memory latency or increase the memory bandwidth. Okay. All right. So anyway, you can see that a naive implementation of this function will generate a ratio of 1, which is not good. Okay. So how can we do better? Okay. The easiest way is through the shared memory. Okay, as we mentioned. So for shared memory, as we know, when we introduced the shared memory, we already told you that the way to use shared memory is very simple. Just load your data to the shared memory, right? With a memory assignment operation, then you can move the data from global memory to the shared memory. And then you can replace, right, the memory pointer to your global memory with the pointer to the shared memory. So the computation will only perform on the shared memory instead of the global memory. So you can reduce the number of global memory access. Okay? And in this case, that's first of all, just forget about the space limit for shared memory. Just assume that we are able to move all the metrics, all the data from the global memory to the shared memory. So how much memory access do we need, right? If, for example, right, so in this case, for each thread, it should help to move 2 elements from the global memory to the shared memory, because you need to move A and B, right, to the shared memory, because you have 2 metrics. So therefore, each thread here need to move 2 elements, 1 element from each matrix. Okay, and if every thread only need to move 1 element from each matrix, because we have n squared threads, right, to move a matrix with n squared elements. Okay, and the result, of course, after we do the computation, we also need to also need to write the result, right, to the shared memory and move it to the global memory. That's matrix C. But again, read-write can be considered separately. So here we only consider the read. So each thread need to read 2 elements, load 2 elements to the shared memory. Okay, so it still requires 2 global memory access per thread. Okay, but how many computation can be performed by a single threads? Okay. If you look at this code, right, we have n squared threads, but each thread will iterate through n iterations. And the ABC over here will be replaced by the address of a shared memory, not the global memory anymore. So the computation here, all the memory access performed here, they are performed on the shared memory, not the global memory. Okay, so the computation, right? So that's why the memory copy, the global memory access, still only 2 per thread. But in terms of the computation, right, each thread needs to perform, right, 2 operations, as we explained before, for each iteration, and we have n iteration. So in total, that's 2 times n computations, right, per thread. Okay, so so after we use the shared memory, the ratio of CGMA will become n, right? Because that's 2n divided by 2. So that's n. Okay? So that means as long as the size of the matrix is larger than 64, right? As long as n larger than 64, then through the shared memory, then we can easily achieve actually, right, any CGMA we want. And as long as the matrix is larger than 64, then the bottleneck will no longer be on the memory access, or at least not the bottleneck on the global memory. Okay, all right. So you can see through shared memory, as long as you have data reuse pattern like this case, it could be easily increase the CGMA ratio in order to increase your computing utilization and reduce the memory access bottleneck. Okay? However, that's just the ideal case, because you can see here, in order to achieve the target ratio, we need n larger than 64. And if you really calculate the size of the shared memory you need, you will find that actually you will require 12 megabytes of a shared memory, okay, on a single, let's say on a single block. That's the size on each string processor. And that's actually way larger than the the shared memory size could be provided per block or per string processor according to the hardware spec. If you look at the spec, okay, usually it's about we mentioned a couple of 100 kilobytes only. So it's way smaller than the 12 megabyte we need over here. Okay, and how did we get this 12 megabyte? Right, you can simply just depend on your code, of course. But here we need to move, right? We need to store matrix A, B, and C, 3 matrices on the shared memory, right? In order to avoid any global memory access from the computation. So each matrix occupy n squared space, right? And and you have 3 matrices. So that's why you have 3 times n squared, okay? And actually each element require 4 bytes. So you need to multiply by 4. So that's how you get 12 megabytes, right? So you can analyze your code to know exactly how much shared memory you need per block. And this number needs to be smaller than the limit from the hardware spec or compute capability. Okay, all right. So as you can see here, although this solution is simple, but most of the time you cannot implement it as trivial as this. No, usually you cannot move all the data you need to share memory at once. Okay. Okay. So how can we solve that? Okay. The way to solve that is to try to load those metrics. We try to partition our data and load them one by one into the shared memory. Okay. And by the way, this shows the pseudocode, right? The complete pseudocode for the solution we just discussed over here. Okay. So the code is, as we just pointed out, basically ABC, right? They are on global memory. And we need to create a shared memory and move the global memory to the shared memory. And then replace the ABC with the shared memory address over here. Okay. And this code is slightly optimized because you can see that actually we only store matrix A and matrix B on the shared memory. We do not store matrix C because we know that the result can be directly written to the global memory, right? We don't need the temporary storage at the shared memory. Actually, we can use only 2/3 of the memory we claim. But anyway, that's still 8 megabytes, still larger than the shared memory size you could allocate it from a single block, okay, from a single thread block, okay. So the problem still exists, okay. All right, and so as we mentioned, how to solve that is to partition your data, okay. And so this is just a concept. Let's just try to illustrate the concept by this figure, okay. So this is what happened for a matrix multiplication, right? As we know, we have to read every row from A and multiply by the column of B, and then take the aggregation to get the result for a single element in the in C matrix, okay. And so since we cannot load the whole matrix of A and B to share memory, so one simple way is to just partition the data, right? You can partition it anyway, as long as you iterate through those partitions and perform the computation that is required on each partition. Then you can always get the same results. You just rewrite your code. And in this case, you can see we divide matrix A by row and divide matrix B by column. And we try to read certain number of row at once to the shared memory and read a certain number of columns from B to the shared memory in order to compute a square, right, in the C matrix. Okay, so Although you can partition it anyway, but here we just to make it simple, we consider a case that's a square matrix, right? And the partition size will be the same for matrix A and B. So all we need to decide is the what we call the tail width. Okay, so tail width is basically the length, the dimension of this square we try to compute over here. Okay, so if a tail width is 2, that means we try to compute a 2 by 2 result from our two input matrices. Okay, and you can see that in order to compute this square, right, we need to load 2 rows from A and 2 columns from B. Then we can compute this region or this blocks, right? Okay, so this is just the concept. So that's why this class of algorithm is called the block algorithm or tailed algorithm. Because basically you have to partition or rewrite your algorithm into a set of blocks or tails. And what you need to decide is the tail width of each of the tail or each of the block partition. Okay. All right. So it's a general concept, and you have to adjust according to your computation to know exactly what's the region or what's the partition need to be loaded from every input variables. Okay, but the goal is to reduce the amount of data we require for computation, right? Because before we need to load the whole matrix, but as you can see here, we only need to load 2 rows from or 2 columns from each matrix. And we can reduce the tail width to reduce the amount of data that we need to load it. Okay. But however, that's of course there's a trade-off, right? With a smaller tail size, usually you lose more data reuse on your shared memory because, as you can easily imagine, some of the data need to be loaded to the shared memory multiple times, right? Before, if we can load the whole matrix, we're supposed to just load every element to the shared memory once. But in this case, you can see, for example, the red column, right? We have to load it when we compute this partition, and we have to load it again when we try to compute this partition. So we have to load it multiple times. Okay, you might think if we load it, although we need to load it multiple times, but it seems like we could resolve that by keep the data in the shared memory, right? Because we need it for those 2 partitions, and if we compute them one by one, then we can just keep the data on the shared memory, right? But that may not be the case if you keep computing. Then you see that it depends on the order of your computation. Sometimes you just have to clean out the space and so that you can load the other data from your matrix. Okay, so it's not guaranteed you can always keep the data in your shared memory. Okay, in the worst case, of course, that means every tail, so every tail or every partition you try to compute, you have to reload the data it needs from your global memory. Okay, so of course that means you have to load the data multiple times. Okay, and that will increase the number of global memory access. Right. Okay, so so that's the concept, and now we look at the code to see exactly what happened and how can we realize that concept in our example code. Okay? So you can see usually it's not hard to realize it because most of the time we use shared memory because we have for loops, right? For example, here we have 3 layers of for loops, and so we try to partition the loops, right? So we can partition it by having the outer loop and the inner loop for every iterators like I, J, K. Okay, so you can see here we have I plum, J plum, and K plum. Okay, and for I, J, K, that will be the tail we mentioned here, right? So we still have I, J, K referring to this small partition, which is called a tail. Okay. And of course, in order to compute the whole matrix, we have several tails, several blocks. So that's why we have the I plum, J plum, and K plum, right? To iterate through those tails. Okay. So it's not too hard to understand, right? So for I, right, originally it should be from I to N, right, with a step of 1. But now we change it to this smaller block, right? So for each I, we only need to iterate from I plum to I plums plus tail width minus 1, right? The smaller block, okay? And so the number of blocks is the size of n divided by tail width, right? So that's, which means the outer loop will have a step of tail width. Okay, so at the end, we just simply rewrite the code. Okay, all right. So so when we after we do this tail algorithm, then when we try to analyze the CGMA ratio, again, we only need to look at the computation and the memory access within a single tail, right? Because every tail just repeating the same thing. So the ratio will definitely remain the same. So we only need to analyze the CGMA ratio from a single tail as shown over here. Okay. And of course, you can analyze many ways, like look at per thread level or just look at globally. You should get the same results. Okay. So here we try to analyze it from the whole across all the threads, because the shared memory, right? When we try to move the data from global memory to shared memory, it is performed globally throughout across all the threads. They move the matrix together. Okay, so here when we try to analyze it, we analyze it from the aggregation point of view, okay, across all the threads within this thread block. Okay, right. So that's very similar to what we analyzed before. Again, let's first consider how many global memory access needs to perform, and you will see that it's basically the same problem as before, but now we reduce the matrix dimension, right? Dimension length from n to tail width. So everything stayed the same. So that means the amount of global memory access should be, right, the tail width square, right? Means that's the every element within this tail needs to move from global memory to shared memory. And you have to move for matrix A and matrix B. So that's why you have to multiply by 2. Okay. And for the computation, right, every thread needs to compute addition and multiplication, as we said before. So that's 2, right? And globally, you have to perform this across iteration I, J, and K, right? And each of them has a iterator with size of tail width. So that's right, tail width to the 3. Okay. So same as before, actually, after you divide it, then you will see the CGMA ratio will be controlled by the tail width. But now the length of the matrix is not the input's power and size. Instead, it is a fixed variable that we configured, right? Called the tail width. Okay, so we can configure to any numbers. Of course, we would prefer the tail width to be larger the better, because that will create a larger CGMA ratio. But at the same time, this ratio, this configuration, this tail width must limited by the size of the shared memory, because we have a limited shared memory size. Okay, so the tail width is actually determined, right? We can determine it by the size of your shared memory. For example, if say the GPU we have is 48 kilobytes shared memory per thread block, then we know that the total, right here we can see that the total memory space we need is needs to be the tail size square multiplied by 3, right? Because we have to store, say we need to store A, B, and C on the shared memory. Okay, so so you can, right, you can compute that the maximum tail width you can allow, right, under this space constraint, right? All right, so so this is just some calculation, right? Then you can get that in order to fit in a 48 kilobyte shared memory, store 3 metrics with the size of a tail width, then the tail width should be smaller or equal to 64. Okay, so the best CGMA ratio we can achieve over here is 64. Unfortunately, that is happen to be the ratio we need to we target on this GPU model, right? This GPU architecture, because it happened that the computing, just a theoretical bound, the computing capability should be 64 times more than the bandwidth, right? The amount of data you need to load. Okay. So in this case, 48 kilobyte shared memory is enough to balance the computation and the memory access. But this, of course, is not always the case, right? It all depends on your computation. After you analyze it, then you can determine the maximum tail width you have, and then you can derive the best CGMA ratio you can achieve with the limited space on shared memory. Okay. All right, so it's just so it's a general principle how you could rewrite your code to utilize the limited shared memory space, and you can follow this to analyze your code to know that how big or how large the CGMA ratio you could achieve under the space limits. Okay, and of course you can always do some optimization, in order to increase this ratio. For example, as we said, we don't need to store C on the shared memory, right? Because the result of A and B can directly return to C on global memory. So here, supposedly, we could divide it by 2 instead of 3. So that will allow us to achieve an even better CGMA ratio. Okay, so it's case by case. Sometimes you could further explore more data reuse pattern or store less amount of data on shared memory in order to achieve a better CGMA ratio. Okay. All right. So this is the general strategy for a tail algorithm. Okay. And this is the complete code for the approach we mentioned. Again, it's pretty much same as before. Is instead of we have n, now we have tail width over here, right? So we break the problem from a huge matrix to many small matrix, right? And try to compute those small matrix one by one on GPU, so that we can fit the problem into the limited memory size. Okay, on shared memory. Okay. All right, so you're going to need this for your homework 3 as well. Okay. Okay, so that's the introduction of a tail algorithm. Okay, and so the key is to try to increase the CGMA ratio. But as we mentioned, usually it is not as large as, it's not larger the better. It's not always the case, because if the CGMA ratio is really big, then maybe you are bounded on the computing side instead of the memory side, right? And also, you can, if you really analyze the amount of computation, you will find that with, if you increase the CGMA ratio, maybe you require to partition your data, and you will require more memory transfer or other constant overhead when you try to do the partition. So on GPU, there's always a trade-off exist. Okay, but in principle, right, we usually analyze the computing and the memory bandwidth ratio as a target, like 64 in this case. And so we only want to reach 64, or maybe slightly larger, but we don't want to, right, push it to maybe over 100 or 200. Then maybe that will not give you the best performance as well. Okay, so it's just an indication. Okay. All right, and of course you can always, it's a tuning parameter, so you can always try to tune the tail width, right? And even you can partition it in different way. You can, you can maybe partition to different, you can use even different partition size on matrix A and B as well. You have many ways to partition the data, and you can always follow what we introduced to analyze whatever the method of your partition, and to also you can try to test the performance and to see exactly which partition or what's the size of the tail width can give you the best performance. Okay, so there's always a lot of tuning you could do for a specific case on a certain GPU architecture. Okay. All right, so that's the introduction of tail algorithm. Okay. All right. Any questions? All right. If not, let's have a 10 minutes break, and we will resume our class at the 4:25. Okay. So we can wrap up this chapter by introducing the band conflict we mentioned on shared memory, and some basic technique like address linearization, which usually will help you to have memory closest on global memory, as well as avoid band conflict on shared memory. Okay. Right. So let's have a short break.